Welcome to the Droidcon Italy webinar. My name is Lucy James. I'm one of the organisers of Droidcon Italy. Today's webinar, you'll be hearing from Daniele Mazzocchi. Hi, Daniele.
Hi, Lucy. How are you?
I'm good, thank you. How are you today?
I'm good, thank you.
How are things looking in Milan?
Yeah, this is good.
Good. Today's webinar, you're going to be talking about geolocation, aren't you, Daniele?
Yeah, and thank you for this opportunity. I'm very happy to be here.
We're very glad to have you. Today's webinar is brought to you by Synesthesia. It is powered by Accenture, and Daniele, have a great webinar.
Thank you. Hi, everyone. As Lucy said, I'm Daniele Mazzocchi. I'm an Android developer at Accenture, and I have been working vertically on Android for about 8 years. I started in Sydney as a freelancer in 2012, and I have been with Accenture in Italy since 2018. In my career, I have often had to deal with geolocation, and I'm here today to share my experience with you because I know we take geolocation for granted, but in reality, it covers a lot of interesting topics. And it is from these interesting topics that I want to start today. So the path we will follow will begin with what we don't see and what is hidden behind this tool. So we will talk about the GPS, GNSS, and I'll show you some neat things. Later, we will go through how the framework works. We will talk about what we can do, and we will speak briefly about Huawei Mobile Services. After that, we will go through the code and take a look at something that you can use during the development phase of your geolocated apps. So what is behind geolocation? I would like to start by showing you something special. Maybe for some of you who are quite passionate about astrophysics, it will be clear. But for some of you who aren't, they are topics that don't come up every day. And so I would like to show you something that is hidden behind the reception of the location. And if we want to find the starting point, GPS satellites are definitely where to begin. As we all know, the best known way to get our position is through GPS satellites. The GPS project was started by the US Department of Defense in 1973, and the first prototype spacecraft was launched in 1978. We had to wait until 1993 to have the full constellation of 24 satellites operational. And today, the GPS constellation is composed of 31 satellites. It is common practice to talk about the GPS to identify all available satellite constellations, but in reality, the United States is not the only country that has its own project. Yes, because other countries also have similar projects, and this brings us to GNSS. GNSS is an acronym for Global Navigation Satellite System, and this is the standard generic term for satellite navigation systems that provide autonomous geospatial positioning with global coverage. So we have GPS for US, and we have GLONASS for Russia, Galileo for Europe, Beidou for China, and also other regional systems. The advantage of having access to multiple satellites is accuracy, redundancy, and availability at all time. Because even if satellite systems don't often fail, if one fails, GNSS receivers can pick up signals from other systems. So you can imagine how useful it is to be able to have access to more than one system. To help you to understand the complexity that lies behind the calculations for the coordinates, I want you to think about some features of these satellites. First of all, a GPS receiver can obtain the location only if it is able to connect to the signal of at least 4 satellites. And you have to think that we are talking about satellites that orbit at a distance of about 26,000 kilometers. And this enormous distance makes the satellite reference system very different from ours. In addition to the distance, another significant number which affects the calculations is the speed. Yes, because each satellite performs 2 orbits around the Earth per day. And to do this, they are moving at incredible speeds of about 14,000 kilometers per hour, which correspond to almost 4 kilometers per second. At this speed, for example, you can travel from London to Paris in just over 1 minute. This incredible speed changes the rules of reality that we know, and even time flows differently. This happens because of a phenomenon that is called the spatial relativistic time dilation. Thanks to Einstein studies, we know that when the difference in speeds of two different objects is very high, the time of the reference systems flows differently. And this is what happens on satellites, because the incredible speed at which these satellites move is high enough to make time flow differently than how it flows on the ground. For example, since a satellite moves at 14,000 km/h, special relativity predicts that the onboard atomic clocks on the satellites should fall behind clocks on the ground by 7 microseconds per day. So time on board a satellite flows more slowly than us by 7 microseconds. And that is not all, because it is not just speed that changes the flow of time, but also the mass of the Earth. Yes, because as we said, the satellites are located very far from us, about 26,000 kilometers above the ground. And there is another form of time dilation that is the gravitational time dilation. From Einstein studies, we know that a nearby object with a significant mass modifies the flow of time due to the space-time curvature. So even in this case, the characteristics of our satellites are crucial. For example, for a satellite that orbits at 20,000 kilometers above the ground, a calculation predicts that the clocks in each GPS satellite should run ahead of ground-based clocks by 45 microseconds per day. So even here, time flows differently, and clocks run faster by 45 microseconds per day compared to our time on the ground. Imagine if the engineers who designed all this had not considered these differences. It wouldn't be possible to synchronize the satellites, and the localization would have been off by many, many kilometers. So, just to recap, do the combination of gravity and speed. On a satellite with these attributes, time goes faster by 38 microseconds per day. But you have to think that there are other things that need to be taken into consideration. Think about the weather or the direction in which satellite travel, the different speeds, different distances, and also many other variables are involved in these calculations. So this is just an example of the difficulties and complexity that an accurate geolocation requires. So we can conclude this first part by saying that we often underestimate the power of the tools and technology that we have available. And now, returning with our feet on the ground, we can go ahead with the Android world. Yes, now let's start the second part of the presentation. And before we begin discussing our project, I would like to show you the relationship between Android devices and GNSS and talk about what the Android framework makes available to us developers and how to optimize the use of the framework with Google Mobile Services and Huawei Mobile Services. As we've seen, there are various constellations of satellites, but do all devices have access to all constellations? The answer is no. No, because their conformation is variable, and depending on the manufacturer, the various GNSS can be different. Here we have some example, and we can see that the Huawei P30 Pro uses GPS, GLONASS, Galileo, and Beidou, while a Samsung Galaxy Note 10 or a OnePlus 7 doesn't have access to the Chinese constellation Beidou. Of course, you can find all various GNSS access configurations on the Android official documentation at the link in this slide. And of course, I can post it on the comment later. So now let's move on to the relationship between the Android operating system and geolocalization. As we know, Android offers all the features to handle geolocation. Already from API level 1, we find the location manager class that provides access to the system location services. Through this class, we have access to a set of very important features like access to the location, check of GPS status, access to various providers or proximity alerts, and so on. But today, many access points to the geolocation system have been deprecated, and it is officially recommended to use the Google Location Services API. The location API available in Google Play Services facilitate adding location awareness to your app. So Google provides us with multiple APIs that can be very useful for developing. And yes, in this slide, you can see some example. The first is Places API, that is a service that returns information about places using HTTP requests. We have geofencing API that allows you to define perimeters which are around the areas of interest. The Fused Location Provider, that is a location API that intelligently combines different signals to provide the location information to your app. We have the Google Fit API, that are new APIs to make building fitness apps easier. And also we have another important API that is the Activity Recognition API that can tell us if a user is in a vehicle rather than if they are walking or running. So there are, of course, also other sets of APIs that I am not listing here, but this is enough to understand why Google suggests using their APIs directly to access the framework's location services. But now, are Google's APIs the only tools to make optimized use of the framework? As we know, recently, there has been a small disagreement between United States and Huawei. Last year, Huawei was added to the entity list after the US Department concluded that the company is engaged in activities that are contrary to US national security. Therefore, now the company can still use Android as an open source operating system, but only by removing critical Google apps and services. But the Chinese giant has not been found unprepared, and thanks to the Huawei Mobile Services, they have been able to totally replace Google Mobile Services. And in February 2020, the first model without GMS and with HMS, the Honor V30, made its debut in Europe. As a support for HMS, Huawei released the HMS Core Toolkit, which is an advanced tool for the Huawei Mobile Services ecosystem. But who could be interested in using it? The first scenario is a scenario where a developer has an Android app with Google Mobile Services and wants to quickly migrate the app to the HMS to release it in the Huawei App Gallery. That is the Huawei App Store. In this case, the HMS Core Toolkit provides a configuration wizard and a useful code converter. The second scenario is a scenario where a developer wants to integrate the HMS into a new app, of course, to release it in the Huawei App Gallery. But in this second case, the HMS Core Toolkit provides the configuration wizard, the repository, and a useful coding assistant. These are two scenarios in which developers may be interested in using the HMS Core Toolkit. So, to facilitate developers implementing, testing, and releasing apps with HMS, Huawei has released the HMS Core Toolkit plugin. The plugin extends the Android Studio environment with functions such as code converter and configuration wizard. But the converter helps developers to automatically convert the GMS API into corresponding HMS API. And this is very useful because you can do it without the need to proceed with the manual reverse engineering of the code. So the HMS converter provides the conversion with two different rules, as you can see in the scheme. The first one is to HMS API that convert GMS APIs into HMS APIs so that your app can run on any Huawei mobile phone. The second one is add HMS API. This option add HMS APIs to your app together with GMS APIs. So this second approach is preferable since the project code base will remain the same and the app will be able to call both GMS APIs and HMS APIs. So guys, as you can see, Huawei has made it easy to add HMS to your application. So don't be afraid to add it and to release your apps in Huawei App Gallery. Now, I would like to show you an example of the use of geolocation by reporting of a development experience that I had in the past. So I would also like to analyze with you the possible solutions to allow a tester and the customer to test our app. And lastly, I'd like to show you some code. So in the past, I have often worked with applications with strong dependence on the system's geolocation. I selected an example in particular to show you how to use geofencing and how to test your app. Sorry. Some time ago, I had to develop an application for a large-scale European group specialized in consumer electronics. This group has many stores in cities all over Europe, and we were asked to implement an app that was able to detect Bluetooth beacons positioned within the store. These beacons indicated to the app how to interact with specific areas of stores. But you know, scanning Bluetooth beacons is obviously a very high consumption operation for the device. Therefore, it was unthinkable to implement an app that would continuously scan for surrounding Bluetooth signals 24/7. So we decided to use geofencing to limit the activity of the scan only in the proximity of the source or inside the geofence. So let me show you how this works. Thanks to this image, you can get an idea of how the application was built. On the map, you can see the various geofences placed in the source. In the zoom, you can see the various beacons arranged by area to which the app had to react and interact. So the user was able to travel the world and the app remained inactive. But when they entered a geofence, the app was able to activate the detection of Bluetooth beacons and react according to requirements. Upon exiting the geofence, the Bluetooth scan stopped and the app went into an inactive mode. So this is just one example among the many in which geofences have proved fundamental. So that was my real case, but it got me thinking, what is the problem with this kind of app? Well, you can have some problems with the final test. Yes, because we can write as many test cases of our code as we want, but for a final test, we only have two options. The first option, you or your client would have to physically go to the places where geofences were configured. Second option, on your project, you can use your emulator, but your customer can't. So the alternative is to download an unknown external app to simulate the position of the device. The first option is a truly definitive test, but can only be done once the app is completed. However, it is unthinkable to force the tester to physically visit each geofence every time a new version is released. The second option is plausible only if we are doing an internal test. Asking the client or an external tester to download an app from an unknown external developer to test is not a viable option. And that was exactly what happened to me. When I presented the second option, the client didn't accept and demanded the implementation of an internal test support module. So I implemented an independent Android module to be integrated only in test releases. The idea was allow the end user to set up a fake path on a map, establish the characteristics relevant to the simulation, such as speed and accuracy, have control of the simulation code so that you can expand or customize it, and of course, give the end customer their own code. As I said, the implementation of the module can be done in such a way as to include only the module itself for a specific build type. In the example, you can see how the module is included only if we have selected the debug build type in this case. Nothing, of course, prevents you from selecting a build variant used for releasing the app to testers. In this way, we can add the module to our project, but when we go to release the app in production, the code of the support library isn't included. With this module, the mock test module, a second icon to handle the position will be present on the phone desktop. To do this, the mock support activity was declared as a launcher in the module Android manifest. This will ensure that once the app is released for your testers, a second icon will be created on the desktop of their device. We will therefore have two launch icons in the debug build variant in our case, one that will be our application, one that will serve to configure our test module. Now, let's start from the highest level to understand how the mock test module works and then go in depth. Let's take the example of the project on GitHub that you will have at your disposal. In the project, you will find a sample app, that is the image on the left, which will be preloaded with the 6 geofences in Milan. On the right, you can see the support app where the tester can set a route indicating the speed and accuracy that they want to simulate. Still on the right, you can see that the support activity has 3 buttons on the bottom. With these buttons, the tester can activate the simulation, and once activated, they can safely kill the app. The simulation activated by the tester will be set on the device, and any application of the device, includes Google Maps or our sample app or any application on the device, will receive the simulation. We can therefore observe the behavior and reactions of the app as it virtually enters and exits the geofence. In this sample app, the entries and exits from each geofence is simply notified through a toast message. Obviously, for your project, you can test more complex functions. Now, let's try to focus on the development module. I would like to explain the architecture of the module by working backwards. So let's start by naming the element that handles the fake position to be sent to the device, the mock location handler. In this element, the positions to be sent to the device are calculated and generated on the device system. This element is managed by a foreground service. Therefore, this service will be signaled with a notification to the user indicating that there is a simulation of the position in action. The foreground service will take care of obtaining the path to be simulated from the mock location repository, which will retrieve these positions from its mock location data source, which will get them from the local data source thanks to a room database which contains all local data. The UI management of the data will take place through the presentation layer that consisting of the mock support activity and its mock support view model. The addition of intermediate positions of the path is managed in this class, the mock support activity. When the tester long clicks on the map, they must insert speed and accuracy in order to arrive from the previous point to these new points. So this new intermediate position will be represented by a marker. In addition to creating the path, from this activity, the tester can handle the simulation by using the buttons on the bottom of the screen. So they can delete the added marker, activate the simulation, pause the simulation, and of course, stop the simulation. The activity is linked to a view model, which is linked to a repository. So with this activity, the user can actively manage the intermediate points of the route by saving them on the database. The activity, in addition to managing the saving of positions, also handles the service lifecycle. In fact, when it is closed, the activity will decide if the service must remain active or not. If there is a simulation in progress, the activity will keep the service alive. Otherwise, it will kill it. So the foreground service is always kept active when the activity is running. During its execution, the foreground service will manage the mock location handler, that is the class that handles the simulation. And there are 3 possible states of the simulation: activated, stopped, and paused. The activity communicating with the service will indicate any changes in status, which will then be communicated by the service to the location manager, which will be responsible for starting, stopping, or pausing the simulation. As I said in the previous slide, in addition of communicating the changes of the simulation states, the activity will decide whether the service must remain active or not when the activity is closed. As you can see in the activity on destroy, if a simulation is active, the activity will keep the service alive. Otherwise, it will kill it. So the activity handles the database indirectly. But how does the service retrieve the positions? The first idea was simply to communicate the positions to the service through the activity, which represented the only entry point for an active access to the database. But I didn't like this option from an architectural point of view, because you have to keep in mind that our service is a star sticky service. So if the service is skilled, the system will recreate it. And we want it to be able to recover our position independent from the activity. So the best option was to allow the service to access the repository and observe database changes through the flow coroutines. In this way, the service would have direct access to the database and at the same time would observe any changes of the positions to be communicated to the simulator. So whenever any changes are made to the database, independent of which row is changed, the query will be retriggered and the flow will emit the locations again. So even if the locations table gets updated by the activity, the foreground service will receive the latest info. Okay, so now it's time to see how the mock location handler works and how it simulates the position. The mock location handler provides a management interface of the location handler by exposing a set of functions. We have the set map points, that is a function to update the intermediate map points on the mock location handler instance. We have the status live data, that is a function to expose a live data for outside observers who would like to be updated to the position set by the simulator. In this case, since the position is sent to the device, to the old device, even the classic system location updates work correctly. This function can be used to observe the behavior of the simulator when a position is sent to the system. So at that moment. Finally, we have three functions for managing the activation, the stop, play, and pause of the simulation. The set map points function takes care of setting the various intermediate points on the locations variable of the mock location handler instance. This step was crucial. You must think that in order to simulate the change of position from one coordinate to another, it is necessary to calculate all the intermediate points between the two coordinates and emit them at regular intervals. The simulator is specifically built to update the position of the device every second, for example. So you have to think that after 1 second, it has to update the position with the coordinates calculated by taking distance and speed after this second. After 2 seconds, it has to update the position with the coordinates related. After 3 seconds, same, and so on. Initially, what I considered doing was to immediately set all the coordinates to be traveled within the instance. Obviously, you have to think that if you simulated a 1,000 route at walking pace, let's say 5 kilometers per hour, there would be thousands of intermediate positions. And this is why I decided to save only the intermediate points within the application, and calculate each intermediate position one after the other at time of the mission. The function activate takes care of activating the simulation and emitting the fake position. So before starting to emit the position, this method activates the flag to allow the app to change the location of the system with the mocked location. The function to do this, as you can see in this slide, is the set mock mode. That is a function exposed by the Fused location provider client. Of course, to activate the mock mode, you have to ask the user to enable the app to mock the location on the device settings, because we are going to change all the location for the whole device. Once the ability to simulate the position of the system has been activated, the calculations will begin and the mock location handler will issue the position to the next coordination. So to calculate the location to be issued, I created an extension function of the mock location object. That is the object used internally as a location. The name of this extension is get next coordinates to destination. Before showing you the calculation of the single coordinates, I would like to introduce you this very useful class provided by Google, the SphericalUtil class. This class will be very useful if you have to do calculations using coordinates, because as you know, the Earth is spherical. So the calculation between the coordinates is therefore very complex in terms of geometry. Using the SphericalUtils, you can compute distances and areas based on coordinates. So let's see the methods that I used on this project. The first one is compute distance between, that returns the distance in meters between two coordinates. The second one is interpolate. This function returns the coordinates of a point that lies a given fraction of the distance between two given points. In my case, I used this to divide the path between 2 points at the time of emission. So now let's see the get next coordinates to destination extension. This is an extension function that receives the coordinates to reach, the speed, and the update time to emit the position. And at the end, it returns the subsequent coordinates with respect to the instance of the mock location object on which the extension function is being executed. In this extension, I used the Google library of SphericalUtil first to calculate the distance between the two coordinates, and then to calculate the coordinates to be returned based on the fractionation of the distance itself with the interpolate function. So at each emission, I first calculate how many coordinates are missing to get to the destination based on update time and speed. Then I divide the distance with this number and calculate the first coordinate that I should find on the path to destination. So in this way, I can set on the system the coordinates I should be at that moment. So we looked at the architecture of the module and understood how the simulation is handled through the main interface functions. Basically, once the simulation is activated, up to any stop and pause signal, the mock location handler will continue to change the position of the systems every second using the functions I showed you earlier. So to summarize the architecture, the activity through the user interface is responsible for updating the simulation states and creating the path. These modifications are saved through the various layers of the clean architecture on a room database. This database is observed and queried by the foreground service through the access to the same repository. The activity manages the service lifecycle and its status changes. The service manages the mock location handler that takes care of simulating the location on the device. So this is the module that you can download, use, and now, of course, after this presentation, if you want, customize. Please give me your feedback if you have. So we have come to the end of our geolocated journey. We started from space and from a very different reality from the one we know and experience every day, a reality where space and time are one thing and are not constant. We touched a bit on didactics and talked briefly about a topic that is more relevant than ever today, that is the HMS topic. So, and also we see how to technically integrate HMS in your apps. Finally, we saw how to simulate a position on the Android system, and we looked at an Android module that can put your tester in a position to work better. In this slide, you can find the link to access the GitHub project. Of course, I'd love to get your feedback on it, so please don't hesitate to contact me if you have any ideas on how to evolve the project. Thank you for your time, and yes, if you have any questions, I would be happy to answer them.
Thank you so much, Daniele. Thank you very much for your presentation.
Thank you, Lucy.
There were some really interesting points in there. I'm not a geolocation expert, so I'm not going to. I could point out a lot of it was new for me, but it was really refreshing to hear some of the information that you shared with us. Thank you. I would once again like to thank Accenture, who supported this webinar. Thank you very much. And this webinar was brought to you by Synesthesia. There's time for questions now, Daniele.
Okay. Okay, so let's see. Okay, the first one is, do I need to add lines of code to my project in production to use module? Good question, and that was a very and a very important part of the presentation and the module itself, because you don't have to add any line of code, because inside the mock test module, there is an activity that is declared as a launcher activity. So you can handle the map and the simulation by that icons that will be present on your phone desktop. The only thing you have to add is the dependency, but if you add the dependency with the naming correct, by using the naming build variant, for example, you can, you won't have the project in production. You will have the project only if you are releasing that build variant. So, okay.
Thank you very much, Daniele.
Okay.
I don't know if we've got any other questions coming at the moment.
Okay.
I don't see anything on my side, Daniele, do you?
No, I think...
Okay. I expect you've probably given people lots to think about, and you'll get follow-up instead.
Yes,
Okay.
yes, of course. So you can ping me on LinkedIn or wherever you want. I can add maybe some link on the comments on YouTube, some link related to the GPS and relativity. That is a very interesting topic, and also I can add my contact on the comments.
Perfect.
So you can ping me whenever you want.
Perfect.
Thank you.
That sounds great. Thank you so much, Daniele, and we'll speak again soon.
Thank you very much.
Bye-bye.
Bye.